Now we're live.
All right. Welcome back, everybody, to last but not least talk of the day. So we're very, very pleased to have with us Dr. Danielle Bassett, who's going to give the final keynote of the main conference 2020. So Danielle has an impressive CV and list of awards. So she is the J. Peter Skirkanik Professor at University of Pennsylvania, with affiliations in the departments of bioengineering, physics and astronomy, electrical and systems engineering, neurology and psychiatry, no less. She received a PhD in physics from the University of Cambridge as a Churchill Scholar and as an NIH Health and Science Scholar. Following a postdoctoral position at UC Santa Barbara, she was a junior research fellow at the Sage Center for the Study of the Mind. She is most well known for her work blending neural and systems engineering to identify fundamental mechanisms of cognition in disease and human brain networks. She has received multiple prestigious awards, including American Psychological Association's Rising Star in 2012, Harvard Higher Education Leader, and most recently an Erdos Rainey Prize in Network Science. Today, she's going to talk to us about state transitions in matter and mind. And with that, please take it away, Dr. Bassett.
Wonderful. Thank you so much for the invitation to be with you all today. I am excited to tell you about some of the work that we've been doing in the context of state transitions. And I wanted to give a brief outline of what I'll be going over in the next few minutes. Number one, I wanted to start with developing a theory for the dynamics of state transitions. So I like to start with theory. Then we're going to move into using that theory to probe executive function and dysfunction in a human brain. And then in the third section, I want to extrapolate from state transitions in brain, which is a bit of matter, to state transitions in mind. And there I'll be talking about some newer work that's more on the science of science side of the world. So to get started, I wanted to motivate the work with this passage from Aristotle's Metaphysics, Book 7, where he says, "Mind thinks itself because it shares the nature of the object of thought, for it becomes an object of thought in coming into contact with and thinking its objects, so that mind and object of thought are the same." And I love this passage because it makes me wonder, well, how can mind become? How can mind become an object of thought? And in some sense, it's because mind is or becomes matter. But how does mind actually do the becoming? Well, we can think about how mind becomes as the brain representing objects, events, experiences, or concepts. So let's imagine that the mind has three different mushrooms that it's imagining, and it represents or becomes matter by representing those mushrooms as a pattern of activity across neurons. So state 1 is the representation of this mushroom, state 2 is the representation of a second mushroom, state 3 is the representation of the third mushroom, and each has a different pattern of activity that represents that object. Now, the capacity to undergo a state change from one of these objects to the next provides flexible and actuatable function for the humans. But the key challenge is really the magic of state change. How does one state transition into another? How does our representation of one object move into the representation of another and another and another? And while that may feel quite abstract, I want to make the question very concrete. What features of neural systems constrain which transitions happen and which transitions cannot happen? Or which transitions are easy versus which transitions are difficult? So let's think about that a little bit more precisely. Let's imagine, or let's not imagine, let's state that a pattern of activation across neural populations or neural units is the state of the brain or the state of the neural system. So here I have a picture of a pattern of activity. That's the vector at the top. The darker colors mean that the regions are active. The lighter colors mean that the regions are not active. And underneath of it, I'm showing you the pattern of structural connectivity between those neural units. So we have a little cluster on the left-hand side, a cluster on the right-hand side, and then a chain in the middle. Each of these dots represents a neural population or unit. An edge represents a synapse, and the color represents the activity of that unit. So active neurons can spread their activity to other neurons around them, and specifically to neurons that are connected to them. So having an active population is easy if the neurons in that population or the neural units in that population are connected. That fact actually helps us to understand which states of the neural system are easy and which states of the neural system are difficult. So I want you to focus on the top left, and here I show you a pattern of activity and then a network architecture underneath. This is a relatively easy pattern of activity for this network to produce, because it only has to activate neurons or neural units that are connected to one another, and then it deactivates units or neurons that are over here on the right-hand side. And the separation between the active units and the inactive units allows that separation to be easy. Now I want to contrast that example with a state that would be difficult for a given network architecture. So on the bottom, I'm showing you the same state, but that state would be difficult if the network underneath was a highly connected, non-modular system. So each of these what were modules become densely interconnected with one another. That dense connectivity makes the distinguishing action of active and inactive much more difficult. Another very difficult combination of activation state and network is the one that I'm showing you on the bottom right. So here I have each neural population or unit active and then inactive, active and then inactive, active and then inactive. This is actually quite a difficult state to obtain and maintain if you have the network architecture that is clearly modular. And why am I saying that something is easy versus difficult? What is the mechanism that I'm sort of implicitly using to say that a certain state is easy versus difficult? Well, it is the amount of control that is required, not just to hold that state, but also to transition between different states. So I want to mention transitions before then I then mention the precise mechanism of state change. So on the top here, I'm showing you a transition that is relatively easy, and that is having two populations, one active and inactive, and then switching them so that this one is inactive and then this one is active. That transition is relatively swift and easy, or can be, because the units themselves that share an activation state are densely interconnected with one another. Now let's look at the bottom row, where there are two different patterns of activity that are difficult for this given network to show. And in transitioning from the left to the right, I'm switching every on population to an off population, and then on and off and on and off and on and off. That transition is quite difficult. Now here's the mechanism. Well, the mechanism is, what is the number and strength and extent of the control signals that I need to use in order to induce these state transitions? Well, on the top, I just need a single inhibitory control signal to target the leftmost module to turn it off. And I need a single excitatory control signal to turn the right module on. In the bottom, if I want to transition every single unit to its opposite, then I need a separate control signal for every single unit. And that means that this transition at the bottom requires more control signals injected to more precise locations in the network in order to enact that transition. And that's what makes it difficult, or that's how I'm using the word difficult. So those pictures were to give you a little bit of an intuition for why and how a network architecture of a neural system, whether a real neural system or an artificial neural system, constrains the kind of states that that system can easily attain, or the kind of states that that system cannot easily attain. Now that you have that intuition in your mind, I want to formalize the intuition with a little bit of math. In particular, I want to talk about network control theory, which is an area of systems engineering that I think is really useful for us to understand state transitions in real and artificial neural systems. So in the very, very simplest version of network control theory, what we want to do is to understand not just the pattern of connections between units, but also the kind of activations that are possible and how those activations may evolve over time. So the very simplest model of dynamics that you can write down for that purpose is this one that I'm showing you here, which is just a noise-free, linear, discrete time and time invariant network model. On the left-hand side, I have X being the state of the brain at time t plus 1, and that's equal to A, which is a weighted adjacency matrix, times the state of the brain at time t, and then plus the control. So B is a matrix with ones along the diagonal where energy will be injected, and U is the control energy that's injected into those kappa regions at time t. This is a way for us to start to understand questions about how states exist, whether they're easy to obtain, and whether they're easy to transition among. Now, to explicitly quantify the ease or difficulty of a given state transition, I want you to focus on the left-hand side picture where I have an initial state of the brain of activation of motor cortex, and perhaps we want to transition into an activation of visual cortex, and that's where you see this strong purple along the back of the brain. So our question is, how do we move from state x0 to state xt, where both x0 and xt are well defined, instead of following the normal trajectory that the brain may typically follow to this gray activation state? Well, to answer this question, we can begin with that simple model of network dynamics that I just showed you, and we can define a cost function that penalizes the control energy that is required and the distance of the current state, x of t, from the target state. And that penalization helps us to go close and more linearly to the target state. So this is the minimization that we could write down and that we do use for much of the work that I'll show you. So here we have the state of the brain, the target state, minus the current state. And then this term is just helping us to fine-tune or minimize the distance of the current state from the target state. And the second term here is the control energy. So by minimizing this entire function, we're minimizing both the distance and the energy required. So with that in mind, we can start to think quite conceptually and then more practically about the energy that is associated with a given state transition. So if I have this activation state over here on the left, and I want to move to a new activation state, I can ask, what is the minimum energy that is required to enact that state transition, given a model of dynamics and given a network structure? And the model of dynamics we can make more complicated than the simple linear one, and the network structure can be one that is given to us in a true human brain or is defined by us in an artificial neural network. But the key sort of take-home of this approach is that the network architecture of the neural system constrains which transitions are easy with a small minimum energy versus which transitions are hard, so a large minimum energy. Now, it can also allow us to ask questions about maintaining a given brain state. How much energy would be associated with maintaining a state of high cognitive load, for example? And how much energy would be required to maintain a state of low cognitive load? So to persist in a particular state also requires energy, particularly if that state is not an energy minimum on the accessible landscape of the dynamical system. So with that sort of conceptual and a few bits of the math before you, I want to dig into a few examples using this approach to understand and probe executive function and dysfunction in humans. So first I want to ask, what sorts of transitions are important for our brain? So the transitions among mushrooms may not be so important. Maybe there are different transitions that are important for a brain to enact. What kinds of transitions might be important? I think the answer is many. An interesting question is, how do we understand not just the transition from state 1 to state 2, but the transition from state 1 to a whole class of target states? And that's where I want to focus your attention right now. How do we understand moving from one state to a whole class of target states? And to do that, we can write down two different kinds of control strategies, which are this one-to-many approach. Both of them are based on that simple linear model of dynamics that I explained to you earlier. And then also from that, we can write down the T-steps controllability Gramian W, which I'm giving you here, which, as you can see, is a function of both the adjacency matrix, so the connectivity among neural units, and also the B matrix, which tells you which units actually are allowed to have energy injected into them. The first kind of control strategy that we can use from these two equations is the average controllability, and that's defined as the trace of the inverse of the Gramian. And that allows us to quantify the ease with which the system can move on the energy landscape, and particularly to many nearby transitions. The modal controllability, on the other hand, is a separate kind of strategy that, again, is kind of from where you are to anywhere else. Or not to anywhere else, but to a particular set of target states. And that's defined straight from the eigenspectrum of A. So we can let the element V sub j be the jth eigenvector of A with a particular eigenvalue lambda j. And then if the element Vij is small, then the jth mode of the system is poorly controllable from node I. That allows us to define a measure, phi I, which is a scaled measure of controllability of all n modes from region I. So you can see we're summing over all n modes from j equals 1 to n, using both that smallest element of Vj and also the eigenvalue lambda j. This allows us to understand which modes are poorly controllable. In other words, how can I push the system from where it currently stands to a more distant state far away on the energy landscape? These two particular kinds of control strategies are useful in understanding the potential for control that different areas of the brain display. And I want to contrast two particular kinds of areas. One is areas in the default mode system, which here I'm highlighting in dark blue. And another set is areas in the frontal parietal or cognitive control or executive system regions. So in the blue, these default mode areas, what we find is that the controllability of those regions is mostly average controllability. So they have the capacity for pushing the system into many of the places nearby on the energy landscape that the system can reach, whereas it has relatively low modal controllability. And we see the opposite in the frontal parietal system, where we actually find very high amounts of modal controllability and very little average controllability. Now, what does that mean, and how does that help us to understand executive function in humans? Well, what we find in these green areas is that the regions that are important for transient control processes necessary for normative executive function are regions of high modal controllability and are therefore structurally predisposed, based on their white matter architecture, to be able to push the brain into difficult to reach states. Whereas regions that are active at rest, so regions of the default mode system in the human, show white matter connectivity patterns that are predicted to drive the brain to nearby states on the energy landscape. So this is a distinction between the types of control that these regions are predicted to be able to enact given their white matter connectivity or their structural connectivity. And we can think about how we would use that distinction in artificial neural systems as well. Now, the next question that we wanted to ask in probing executive function as a kind of control that's intrinsic to a human real neural system is to study the time span in development over which executive function changes appreciably. So for this part, we studied youth who are between the ages of 8 years old and 22 years old. And we asked, how much controllability do these brains have? And does it change with age as executive function is developing? So we sort of think of development as a natural perturbation of the network topology. Is controllability preferred? And if so, how? So here, every data point here is a person inside the Philadelphia neurodevelopmental cohort, and the values along the y-axis are the modal controllability per subject. The values along the x-axis are the average controllability per subject. And so what you can see is that average and modal controllability are correlated with one another, meaning that brains that have high average controllability are able to enact that strategy well, are also the regions that have high modal controllability and are predicted to enact that control strategy well too. Both of these types of control are greater than expected in null models. So in the yellow here, I'm showing you null models preserving node strength, which is the average connection strength coming out of a region. And then in the peach, I'm showing you a null model that preserves node degree, or the number of connections that are coming out of a given region. And then lastly, what we found in this study is that both types of control increase with age. So in other words, the people who are up here on the top part of this graph are the oldest youth in the study. So that indicates that as youth move from 8 years to 22 years and their executive function develops appreciably, we also observe that their controllability capacity changes given reconfiguration of the white matter structure. So this is a correlative finding. It's a nice piece of evidence, but it is not a direct proof that executive function comes about by network controllability. So to sort of probe more deeply and see if we can get closer to answering that question, I want to ask whether we can be more precise about the transitions that might be relevant for executive function. Maybe executive function is not the ability to move from a given state to any possible state far away or nearby. Maybe executive function is much more about activating a particular state in the human brain. So I want to gray out all of these other activation states and just focus on activating one particular state. And again, I will be using this approach that I showed you earlier to quantify the ease and difficulty of state transitions by minimizing this cost function that penalizes both the control energy over here on the right-hand side and the distance xt from the target state. Now, the particular state transition that may be relevant for executive function is activation of the regions that are important in cognitive control, and that is the frontal parietal system. So I'm showing you that pictorially here, where we have an initial baseline of the brain with no activation, and then activating the target state of frontal parietal circuitry. This is work that was led by Jaju, and he was working in Professor Ted Satterthwaite's group when he was doing this work. We study 946 youth, again between the ages of 8 and 22 years old. This setup allows us to isolate the effect of activating the frontal parietal system, and we are studying the white matter networks that are subject specific. So for every single youth, we're using their particular connectivity pattern measured from diffusion tensor imaging acquired in the same subjects. What we find is that easier recruitment of the frontal parietal system occurs as development proceeds. So on the x-axis here, I have the age of the youth in years from 8 to 22, and along the y-axis, I have the control energy for activating the frontal parietal system. And you can see that there's a negative relationship here, indicating that control energy less control energy is required in older youth whose executive function is already well developed. So this evidence supports, but again does not prove, the idea that white matter network architecture in a real human system develops to ease the transition to executive function, thus facilitating the frequent use of this cognitive process in older youth for working memory, for decision-making processes, and for inhibiting inappropriate behavior. We also find that control energy is directly associated with individual differences in executive function. So after removing the effects of age, we studied the control energy along the y-axis here, and along the x-axis is individual differences in executive performance as measured from a factor analysis of a 2-hour computerized neurocognitive battery. You see a negative relationship here. What that indicates is that humans that perform well in executive function tasks require much less energy to activate frontal parietal circuitry in this model than humans that have less executive function performance. Importantly, we also noted that the bilateral middle cingulate mediates the relationship between age and executive function, suggesting that the control capacity of that region allows us to better understand how executive function changes as youth develop over this particular period. Now, of course, we can try to understand how a state changes from an initial state to a final state, but I also want to go back to this idea of state persistence. How do we hold in mind a given state for a long period of time? And there may be different energetic requirements for those two different cognitive processes. And in order to ask questions like this, Erzbron studied the transition during a task that requires low cognitive load to high cognitive load. And this was work that was done in collaboration with Professor Andreas Meyer-Lindenberg and Heike Toast at the Central Institute of Mental Health in Mannheim, Germany. And so he asked the question, well, how much energy is required for a human brain to move from a low cognitive control state, like the 0-back working memory performance state, to a high cognitive load state, like the 2-back working memory performance state? And importantly, this task is one that sort of canonically assesses executive function. So on the right-hand side, what you can see is the control energy along the y-axis, and then along the x-axis, you see the comparison of transitioning from the 0-back state, so the low cognitive control mode, to the 2-back state, and then the opposite transition from the 2-back state to the 0-back. And what you can see is that the control energy required to move to the high cognitive load state is higher than the control energy required to come back down to a low cognitive control state. So this suggests that transitioning to a more demanding state requires more control energy than the opposite transition, providing some face validity for the computational modeling behind this assessment. But what happens when we want to hold the 0-back state, so the low cognitive control state, or we want to hold the 2-back state? How much energy is required? What you see here is along the y-axis is the stability, and along the x-axis is either the 0-back or the 2-back. So what you can see is that the 0-back state is much more stable. It requires less control energy to hold it there than the 2-back state. And that is interesting because the 2-back state is a more demanding cognitive state, and so you might imagine that it requires more energy even in a metabolic sense. But here we show that it definitely requires more control energy to hold it, given the pattern of activation required for the 2-back and the pattern of white matter that allows that activation pattern. We also find that greater stability in the 2-back state is associated with individual differences in higher task accuracy. So the more accurate individuals were those who had greater stability of the 2-back state. And in a last assessment of the sort of mechanisms of the control energy and its relation to executive function, Urs examined the relation to dopaminergic signaling. And here in particular, he studied a randomized placebo-controlled double-blind pharma fMRI study, so previously acquired data, that used amisulpride, a selective D2 agonist. What we found in this case is that drug increased the control energy for both transitions versus placebo. So here you see the control energy along the y-axis from 0-back to 2-back, and it is significantly higher in the amisulpride condition than in the placebo condition, and it's the same 2-back to 0-back. Now, this is interesting because by implicating dopaminergic signaling, it also suggests to us that psychiatric conditions associated with alterations in dopaminergic signaling should show differences in control energy as well. And so Urs went further and asked, in schizophrenia patients who are marked by dopaminergic abnormalities and deficits in executive function and alterations in structural connectivity, what happens with the control energy? He finds that the control energy, when transitioning into working memory conditions, the high working memory load condition, the 2-back, is increased, but not vice versa. So in other words, more energy is required to move up to the high cognitive control position, but no additional energy is required to fall back into the 0 condition. So the take-home message from this sort of part of the talk, before I will go to the third section, is that the network architecture of neural systems constrains which transitions are easy, so requiring a small change in energy, versus which transitions are hard, so requiring a large transition in energy, with relevance for development, as I showed in the first study, for disease, and for drug, as I showed in the second study. So that brings me to the last point that I wanted to make, which is to extrapolate some of these ideas of state transitions in the brain to state transitions of the mind. And to motivate this part, I wanted to read a passage from Arthur Benson's biography of Rossetti. get a little bit of literature in here on your Wednesday afternoon. So he says, we find such lines as the unfettered irreversible goal or sleepless with cold commemorative eyes. Note such textures as, oh, what is this that knows the road I came? The flame turned to cloud, the cloud returned to flame, the lifted shifted steeps and all the way that draws round me at last this wind-warm space, and in regenerate rapture turns my face upon the devious coverts of dismay. Or, ah, who shall dare to search through what sad maze thenceforth their incommunicable ways follow the desultory feed of death? So Benson is quoting Rossetti's passages here, and then he comes back and has a little bit of critique, and he says, it will be observed in these last quotations, there is a certain slight shifting of the usual meaning of words like commemorative or regenerate and incommunicable, some slight nuance added to them, which is not found in ordinary speech. This preciosity has a charm of its own, and upon this handling of language, this delicate straining of the use of words, depends much of the pleasure derivable from the works of masters of elaborate style. And I love this because it makes me think that transitions in brain states require energy, but also transitions among words or the meaning of words may require energy and may be impacted by what's happening around them. In the context of the brain, it's by the network architecture of the white matter. In the context of words, the meaning of words, it may be in the network architecture of language surrounding it in a given passage. So that makes me think, well, what are changes? What are drivers of change in meaning, transitions, state transitions in meanings and in concepts? Well, those drivers could be in a single passage, as we just saw in Benson's Rossetti. So what is happening around a word can strain the word's meaning. But we can also see it over longer timescales. So a whole book or a whole culture, there can be that context that strains or changes the meaning of a word over time. And just to give you a few examples to make this a little bit more concrete in your mind, I want to talk about three, one in curiosity, one in society, and then one in science. And in curiosity, I want you to think about the word imply. So in the 14th century, imply meant to enfold or enwrap or entangle, but the meaning of to involve something unstated as a logical consequence was first recorded around 1400. And that of to hint at, which is how we sort of use it now, is from around the 1580s. Now think of an example related to society. Here's a word that again has changed its meaning. Impertinent. In the 14th century, it meant unconnected or unrelated or not to the point. But the sense of rudely bold, uncivil, and offensively presumptuous is from the 1680s, and it's from the earlier sense of not really appropriate to the situation, which came about in around the 1580s. So you can see from these two examples that the 1580s is the time to be alive when all of the words are changing their meanings. But lastly, I wanted to mention a word in science, which rather than having changed a meaning, I think really needs to have its meaning changed. And that is the meaning of the word scientist. So there are a lot of studies in the field at the moment that suggest that in our minds, in all of our minds, no matter what gender we are, what race or what ethnicity, we have a conception of a scientist as someone who is masculine. So for example, in this paper that was published in 2016, the investigators did a study where they showed pictures of actual faculty members in STEM, in elite universities, to a set of participants. And the participants rated each of these pictures for masculinity and for femininity, so both the women and the men. Then they took a separate set of participants and asked them to rate each of these pictures for the likelihood that these people were scientists. Note that all of these people actually were scientists. They were pictures taken from actual faculty profiles at elite universities. The participants in that group assumed that the more feminine-looking women were more likely to be childhood educators, and the more masculine-looking individuals of both the feminine and the male groups were more likely to be scientists. So this is just kind of an implicit bias that we all hold, that masculinity is something that's associated with the meaning of the word scientist. But we also have an association not just of masculinity, but also of the actual gender of being a man. So this is work from 2019 that was published in Nature Geoscience. where the investigators studied 1,224 letters written by 452 applicants, so averaging about 2.71 letters per applicant, by 1,101 recommenders from 54 countries over the period 2007 to 2012. And what they find is that women applicants are only half as likely to receive excellent recommendation letters versus good letters. So the women were described as having a solid skill set, a good track record, strong knowledge, being intelligent, they had an aptitude for learning, in contrast to the men who were described as being brilliant, rising stars, pioneers, geniuses, and trailblazers. But lastly, the meaning of scientist in our culture, and again, this is held by all of us, is not just being masculine or being a man, but also having a man-gendered name. And this is work by Corin Moss-Racusin that was published in the Proceedings of the National Academy of Sciences in 2012, where they used a randomized double-blind study of 127 faculty in physics, biology, and chemistry from research-intensive universities. They sent all of them the application materials of a student for a laboratory manager position. And for each CV, they sent some with a woman's name at the top and some with a man's name at the top, but the identical CV. And what they found is that the application that was assigned a woman's name was deemed as less competent, less hireable, offered less mentoring, and offered $3,007 less in salary than an identical application that had a man's name at the top. And so I wanted to mention this one because it's not just the privilege of an identity, it's actually the privilege of a name separate from the identity. And these studies are just a few that I could have pulled out of the literature. There's very extensive prior work that has reported gender and racial, and I haven't gotten to that point yet, but gender and racial inequalities in academia and industry in terms of compensation, grant funding, credit for collaborative work, teaching evaluations, hiring and promotion, productivity and authorship, and citations. What's interesting about this set of work is that the conversation largely focuses on the role of people in positions of power, like journal editors, grant reviewers and agencies, department chairs, and society presidents, despite the fact that many of the imbalances that are reported are caused and perpetuated by researchers at all levels, including me, just a normal faculty member at a usual, typical university. And one particular example where that is the case is citations. So people from marginalized groups are very broadly undercited by everyone, including you and me, impacting their visibility, potentially slowing or stalling their career advancement, and precluding an unbiased trajectory in the search for scientific truth. There's clear evidence from science of science that we tend to choose new research directions from highly cited papers, and papers that are written by men are cited, and particularly white men, as I'll show you in a few minutes, are cited more than papers written by women and more than papers that are written by racial and ethnic minorities. And third, that means that we tend to answer questions posed by this majority gender and majority race group, and thus the trajectory of scientific discovery and the crystallization of collective knowledge is biased away from the ideas produced by minority thinkers. We really wanted to understand not just the fact that that exists, but what is the extent of that imbalance, and what are the drivers of that imbalance in science, and how can we potentially mitigate it? So our approach, and this is work that was led by Jordan Dworkin, who was a graduate student in biostatistics at the University of Pennsylvania and is now a faculty member, a tenure track faculty member, assistant professor at Columbia University. And what he did is that he examined the authors and reference lists of 61,416 articles published since 1995 in 5 top neuroscience journals. So Nature Neuroscience, Neuron, Brain, Neuroimage, and Journal of Neuroscience. And those were chosen because on the Web of Science, they were indicated to have the highest eigenvector scores. Then what we did is that we assigned the term man or the term woman to each author algorithmically if their name had a probability greater than or equal to 0.7 of belonging to someone labeled as a man or as a woman in the Social Security Administration database or the Gender API. And I want to make a note here about 2 limitations of that approach really upfront. The first one is that in our analysis, the term gender doesn't directly refer to the sex of the author as assigned at birth or as chosen later, nor does it refer directly to the gender of the author as socially assigned or as self-chosen. In our work, that term is specifically related to the nature of the name, and it's a probabilistic assessment based on the name. And then the second point of limitation I want to mention is that the use of a binary man-woman gender assignment is not well accommodated to intersex, transgender, or non-binary identities. And that's a limitation that we hope to overcome in the next version of this work. So just to set the stage of what we found, I wanted to show you this fascinating figure, which collapses information across all 5 journals. And it has the proportion of articles with a woman as a first and last author. So this is the orange bar here. So this is the proportion of papers written with a first and last author who is a woman, 7% in 1995, 10% in 2018. And then in purple, you can see the proportion of papers that have a man first author and a man last author. And you can see that there's an increasing rate of papers that have a woman somewhere in the first or last author position. That increase is roughly 0.6 percentage points per year. Now, we wanted to test the hypothesis of an undercitation of women, as this has been identified in a couple other areas: astronomy, political science, communications, and international relations. So to test this hypothesis, we studied the 31,418 citing papers between 2009 and 2018, and we took the subset of its citations that had been published in one of the 5 journals since 1995. We removed all self-citations so that that wasn't impacting our assessments, and then we calculated the number of cited papers that fell into each of these 4 first and last author categories. So man, woman, or woman. Now, to assess whether a group is being over or undercited, we need to have an expectation of how many citations that group would be expected to get. One simple way that you could do this is by saying that every reference list is kind of a random draw from the proportion of papers out there in the field. And therefore, if there are more men in the field, and as I'll show you later, more white people in the field, then we'll be more likely to pool papers from that group than the minority genders or minority races and ethnicities. So that assessment of random draws is one where we calculated here, representing the proportion among the pool of papers that the authors could have cited. And this 0 line on the right-hand side is that expectation. So that accounts for how many papers are out there by these groups anyway. And then if the actual data diverges from the 0 line, that means that that group is either over-cited relative to expectation or under-cited relative to expectation. And what we find is that papers that have a man in the first and last author category are over-cited by 11.6%, and papers that have a woman in the first and last author category are under-cited by 30.2%. And there's sort of a parametric change as you go down here. So that's a relatively large amount, about a 40 percentage point gap between men and women. Now, the next question is, you probably are all thinking that, my reference list is not a random draw from all of the papers that are out there in the world. My reference list is there are certain papers I'm more likely to cite than others. And that's absolutely true. So we followed this with a more particular model of the expectation, where we accounted for the year of the publication, knowing that we do tend to cite papers in the past when the fields were more dominated by majority genders and races. And number 2, the journal in which it was published. And so that accounts for the prestige even within these top 5. And then number 3, the number of authors on the paper for whether the paper was a review article. And then 5, the seniority of the paper's first and last authors. Now, we don't know the age of the people in our study, so we create a proxy for their seniority as the number of papers that they've previously published. So this 0 line is given by a generalized additive model on the multinomial outcome of those 4 author categories given these variables. And what we find now is that the papers with a man in the first and last author position are over-cited by 5.2%, and the papers with a woman in the first and last author position are under-cited by 13.9%. So about a 20-point difference. So less than what we saw in the random draws model, but still the same overall trend. And the second hypothesis we wanted to test is whether that undercitation was being driven more by one group than another. And again, this is motivated by some work in a couple other fields separate from neuroscience. So here what I'm showing you is the exact same data again, but now separated out into the citing practices of papers that have a man in the first and last author position, or the citing practices of papers that have a woman in the first or last author position. And what you can see is that if a woman is in the first or last author position, or both, those papers tend to cite the groups relatively equitably. So they're quite close to the 0 line, whereas papers that have a man in the first and last author position tend to maintain this skew that you observe here. So that suggests that what we're seeing in the overall population is something that's largely driven by the citation practices of one of the 4 groups. Now, the last hypothesis that we wanted to test in this space is whether this imbalance is increasing or decreasing with time. We predicted that it would be decreasing with time, because the fields are becoming more diverse. But what we actually find is the opposite. So here is the percent over and under citation, again, for papers with a man in the first and last author position. What you can see is that those groups are over-citing other man-man papers increasingly with time and under-citing woman-woman papers more and more with time. So the gap is widening as we go from 1995 to 2018. You can see that that gap is also widening to some degree in the papers that have a woman in the first and last author position, but the increase is, the gap is much smaller. Something we should still be noting in both groups, but the gap is smaller on the right-hand side than on the left-hand side. And so that work made me, all of us wonder whether this was just something about the dimensions of difference of gender, or whether it would expand to other dimensions of difference, including race and ethnicity. So to address this question, we expanded our team significantly and tried to understand the race and ethnicity of these authors, in addition to extending our data set up to 2019. So in this case, we assigned author race and ethnicity, again using a probabilistic approach. So we used a publicly available probabilistic database and a deep neural network that learns the relationship between names and racial or ethnic categories in voter registration data, the US Census, and Wikipedia entries. And the latter is to help us to understand something that's broader than just the United States. The approach allows us to estimate the probability distributions across 4 different racial or ethnic categories: Asian, Black, Hispanic, and white, based on each author's first and last names. Of the 63,000 articles that we studied, the proportion of articles with a person of color as the first or last author significantly increased from 1995 to 2019 at a rate of roughly 0.49 percentage points per year. Then we wanted to ask, well, let's look at the exact same hypotheses again. Is the majority race and ethnicity over-cited, and the minority races and ethnicities under-cited? And the answer is yes. So here's the data relative to the random draws model. You see on the y-axis percent over and under citation. You see an over-citation of papers that have a white author in the first position and a white author in the last position. And you see an under-citation of papers that have an author of color in the first and last author position. And who is driving most of this effect? Well, it's actually people like me, people who are white. So white citers tend to over-cite other papers by white authors, and this is an over-citation of 10.7%, and heavily undercite authors of color by 24.1%. So over 34-point difference, the gap is. And citers of color, on the other hand, tend to have this effect to a much lesser degree. So they still oversight papers from white authors, still undercite papers from authors of color, but to a lesser degree than white citers. And that same trend holds if we use the more sophisticated model that accounts for the year of publication, journal of publication, number of authors, research article or review, seniority, and in this case also the location of the author's institution. So just want you to sort of eyeball that these effects are consistent. Here's the 0 line. Again, papers with a white author in the first and last position are over-cited. Papers with an author of color in the first and last position are under-cited, and that's largely being driven by white citers. And less driven by citers of color. Is it increasing in time or decreasing in time? It's actually similar to the gender gap. The racial and ethnic gap is also increasing with time. And what we can see is that that increase is, again, very heavily driven by white citers, so the majority race/ethnicity. So here you see that white citers tend to increasingly cite other papers from white authors, and increasingly undercite papers from authors of color over this same time period. We can still see a growing gap in the citers of color, but again, it's to a much lower extent. So that begs the question of what's happening in terms of intersectionality. What happens if there's a person who is a Black woman or a person who is a white man? What is the level of over-citation or under-citation? So here you have the first author along the y-axis and the last author along the x-axis. We have men first and then women second. And what you can see just by eyeballing this is that there's a huge main effect of gender. So on average, papers that have a man in the first and last author position are over-cited. Papers that have a woman in the first and last author position are under-cited. But that then we see effects of race and ethnicity inside of each of those blocks, with the papers that are written with a Black woman as a first and last author being under-cited at about 47%. In comparison to papers with a white man in the first and last author position, which are over-cited by 24%. So that's a difference of 70-some percent. So that's a very large gap, which again is increasing with time. So where do we go from here? Just to quickly wrap up. Well, I will be the first to acknowledge that the ethics of citation practices remain to be further defined, and writing social inequalities like this may be accomplished on a number of different models. The distributional model refers to morally proper distribution of social goods and resources, which in this case would be citations. And two submodels in there suggest that these citations should be allocated equally, or perhaps based on merit, need, or authority. I think that distributional model is somewhat limited in emphasizing commodity parity across economies of exchange over our differential responsibility for histories and structures of inequality. And so I personally prefer the difference models, which by contrast recommend acts of reparative justice, which might include affirmative action in citational practices, institutional reform to support citation parity, and disciplinary redress of gender, racial, and ethnic biases more broadly. If you're curious about sort of concrete recommendations, what can I do? We did write an article that was recently published in Neuron that suggests a couple recommendations for scientists that are in different roles, whether they're creators of the science, arbiters of the science, or reflectors of the science. So if you're curious about what we can do, I recommend going to that article. I'll just highlight a few of the tools that the lab is developing for mitigating this disparity, and that includes a citation diversity statement that we're putting at the end of all of our papers that reflects the percentages that we're actually including in our papers. Dale Zoe's GitHub repository, which provides software to predict gender, race, and ethnicity of authors in your reference lists, and you can use it for your own if you wish. Jenny Stizo, who developed a Google Chrome extension, which works with Google Scholar, PubMed, and other search engines. It's called Citation Transparency, and it provides additional information about the authors, predicted information about the authors that you can use while you're searching. And then Max's code in Python, which is sort of a complement to Dale's. So with that, I'll end with the truth is that no one of us can be free until everybody is free. It's time, I think, for a state transition in mind. We need to change the meaning of the word scientist to move beyond a white, cisgender, heterosexual man. The scientist is anyone who is seeking to understand how the natural world works. And so with that, here's the picture of what we did over the last few minutes. As of yesterday, you were over here on the left-hand side. We came here and began with a passage from Aristotle that motivated our theory for state transitions in the brain. We took a transition across Benjamin Franklin in his description of different states that the human may wish to engage in, including habits. We moved into state transitions in executive function, moved across Arthur Benson into a call for state transition in mind, and then ended with Maya Angelou calling us to think about how we might use these ideas in our future being. So with that, thank you so much for listening. I think we still have some time for questions.
Thank you so much, Danielle, for the absolutely mind-blowing talk. I think, I don't know, I was monitoring the comments during your talk, and I think I've seen many times that this was people's favorite talk ever. So that was coming through. We so need to talk about this in principled ways in our community, and this was absolutely fantastic. So we have time for a few questions. So what I'll do is I've been monitoring the questions here. Some are upvoted. I'll go through them. I'll try to balance the questions in between the different topics you covered. But we'll start with the first one, going back towards more the start of your talk. This first question is from Sylvain Bayet. And he asks, isn't controllability of a given network highly dependent on the nature and relative weights of its internodal connections, right? Excitatory, inhibitory, and so on.
Yes, absolutely. That is definitely the case, that the weights matter. Actually, the directionality also matters. So in the first section, I cited Jason Kim's paper that was recently published in Nature Physics, and in that paper we study connectomes that are both weighted and directed. So in humans we don't have directed data, but in the mouse connectome and in the Drosophila connectome we do have directionality. And so you can see in that paper, if you're curious, how directionality changes the predictions. In those two species and at the mesoscale, the amount of directionality is relatively small. And so it doesn't change our predictions a lot. But if we were to go down to the cellular scale, where you have negative interactions versus positive interactions, then absolutely that sign will matter.
Lovely. All right. Very cool. Moving on here, the next question is from David Damaris. Are there more accessible or less expensive biomarkers of controllability for clinical or social settings that you can think of?
That's a really interesting question. I mean, we do show in a recent paper that psychosis spectrum symptoms are strongly correlated with controllability, particularly in transmodal cortex. And so there is a reflection of control differences in our behaviors, but I don't know if that's precisely what you're asking. So there are correlates in neurological conditions and in psychiatric disorders, but I wouldn't use them as a biomarker.
Right. Oh, that's interesting. So in a slightly related topic, there's a question from Arjun Bariok. Sorry again if I don't pronounce your name correctly. How strong is the assumption that the transition is described by a linear equation? So that goes on to sort of control theory, right? Like if you depart from the linearity, how far can you go with these same paradigms?
Yeah, that's a really great question. So you can definitely, in the field of systems engineering, there are really nice examples of where nonlinear systems it's very difficult to come up with analytical expressions for controllability. You can use simulations, but it's very difficult to come up with analytical solutions. And so there's a lot of work there that has shown that even for heavily nonlinear systems, the linear approximation is actually quite good in pushing the system in the direction that you want it to go. And then you may need to do sort of a push and then re-evaluate, push and then re-evaluate, push and then re-evaluate. So you may need a time-dependent linear control approach for the nonlinear systems. That's right. So that's kind of the direction that most of the work goes.
Lovely. Very cool. Very interesting. Next question here from Rakuram. What exactly is control energy? Does it have any neural correlates? So yeah, how do you interpret this idea of controllable energy in expenditures in the brain, for example?
Yeah, that's a really great question. Right now, we're performing a study trying to understand the relationships between controllability and metabolism as measured by PET imaging. So that's an ongoing question in our minds is the control energy really related to metabolic energy? Yes or no, and to what degree, when, how, etc. I'll have to admit that this is an open question we're looking into now, but I don't have a good answer yet.
Right. Okay. Very good. So let me move on. So there was another question here by Junji Jiang, which is quite similar actually. So I'll just pass on here. Another question from you, Liu. Can the theory of controllability be extended to nonlinear RNN? So we've discussed this to a certain extent, but the idea of recurrence, right, can be extended. So you've just mentioned that one can think about them time-dependent linear transitions, right? Is there principles in which you can think about this across longer timescales, for example? I'm taking the liberty to interpret this question a bit.
That's a really good question. So I think I do want to sort of mention where I thought you were going, which was in recurrent neural networks, and can you bring in control there in a meaningful way? So we do have a paper that that's on arXiv if you're curious. It's titled "Teaching Recurrent Neural Networks to Modify Chaotic Memories by Example." And we teach the neural networks to do this by having a specific control signal that's injected into the system and that is kind of moves the system to modify the memories. So it's a neat blend of the two sets of ideas. So if you're in the recurrent neural network space of the field and want to think about control, that's our closest connection.
That's really interesting. I myself am going to check out this paper. It sounds awesome. Here's another question from Ezekiel Williams. Have you explored the relationship between graph structure, state transition, and pattern in driving energy? I expect that the brain might prefer input energy patterns that distribute input energy rather than dumping it into small groups of neurons. And I wonder if certain graph structure might support this better.
Yeah, absolutely. So yes, if you have more than one control point, you can control with much more ease. You require less energy. So you don't want to dump it into a single spot necessarily all the time. Many times if you have access to multiple control points, that's better. An interesting question is what happens in a clinical scenario. The more stimulation points you have, potentially the higher risk for the patient. So there will be, in real clinical applications, you may want to think about not just how much energy is required, but also the limitations of the number of control points you have. But absolutely, the actual graph topology matters a lot. And what matters is having a large range of strengths, connection strengths coming out of each region. So you don't really want to have one-to-one connections where there's only this region only connects to that one. That is really difficult to control in a whole system. And what is also very difficult to control is when you have all of the edges being the same weight. So what you want is a wide variety of weights, and then also a large degree. And that's also in the Nature Physics paper from Jason Kim. What I think is interesting about that observation is that in systems where we can get these edge strengths at more precision than we can in humans, it's suggested in macaques and in the mouse that the edge weights span 5 orders of magnitude. And I think that could be for a reason. That could be because that is precisely the kind of diversity that you need to enact control easily.
That's fascinating. I'd like to pivot a little bit and maybe take 1 or 2 questions with respect to the second half of your talk. So there's a really interesting question here from Jay Pina. Have you thought to look at data on audience attendance based on the identity of the speaker, especially how these numbers are at least visible during virtual talks? Not sure if these data are archived at all, but that's an interesting question, right?
That is a fascinating question, and I will admit not one I have thought of before.
So in this day and age of virtual conferences, this might be something that could be
measured,
to be continued. Yes. And another question here from Juliana. I'm wondering about the roles of social/academic networks of researchers in relation to the citation diversity work. Do you think these networks have an influence on over-citation, particularly because the over-cited groups seem to be driving the over-citation effects? And do you think expanding on these networks could be a way to intervene on these disparities?
Yes, I'm so glad you asked that question. The pieces of data that I didn't show you from those 2 papers are related to the role of co-authorship networks in explaining the citation patterns. Our co-authorship networks we're using as kind of a proxy for the social space that people work in. And so what we find is that someone who has over-representation of one author group in their co-authorship network tends to oversight that group even more. So our citations are often to our co-authors or to our one step removed co-authors or further on the co-authorship network. And so if there's an over-representation of one kind of person, either a gender, racial, or ethnic identity, in our nearby groups, then we tend to oversight that group even more. So yes, one thing that you can do is to expand your social networks, but also your co-authorship networks and the people whose work that you know. I think that this is really a call for all of us to educate ourselves about the work of minority scholars that maybe we don't hear because maybe they don't get invited to give the talks, or maybe they are not published in a given journal for other reasons, because we know that there's a lot of bias that occurs in peer review too. So I think it's up to us to spend some time consistently throughout our lifetime, educating ourselves about the work of everyone and evaluating whether it's relevant to be cited in our work.
Absolutely. Wise words here. And you need to broaden this feedback, right, to break this little clique system that we're getting. I'd like to maybe pivot back to a last question, which I've did not attend to here, with respect to your first half of the talk. And this is a question from Jinendra Ekanayake. She or he says, just a wonderful talk. My question relates to the changes of energy landscape during neurofeedback related to learning effects. Can Danny comment on this?
Yeah, that's a really great question. The closest that we have is a paper that is using brain-computer interfaces and the learning of brain-computer interface. So why and how is it that one person can learn how to use a BCI really well and another person can't learn to use a BCI really well? And that paper was recently published in Journal of Neural Engineering this year. The first author is Jennifer Stizo, actually the person who created the citation transparency tool for Google Scholar. And she uses the control approach to predict why and how one person would be able to move, in the learning trajectory and another person would not. So I think there is a connection here. Precisely how that relates to neurofeedback more generally, I think is a very open question.
There might be links to there's some more invasive BCI work of within and outside manifold learning, right? That might relate to this. Open questions here. Lovely. So I think in the interest of time, we'll end this here. Thank you so much once again for giving this amazing talk, and thanks again to all of the speakers of today's session and throughout the 2 days of scientific talks that we've had. I remind everybody that tomorrow there's an educational day with amazing tutorials. And I will also invite everybody here to go to the Gather Town for a great social and networking event. I'll remind everybody that if you'd like, we encourage you to include your preferred pronoun in your name so that it makes it easier to interact and more inclusive interactions in the Gather Town environment. And with this, again, Danielle, I would like to, on behalf of the entire main community, thank you once again for joining us. And we'll see everybody in Gather Town. Bye-bye.